Hello, good morning everyone. Today we'll look at the last topic of greedy algorithm, which is, sorry, I think my mic is still off. Hello, good morning everyone. Today
Morning,
we'll,
sir.
yeah, good morning. So I'm audible, good, thanks. So today we'll take up the last topic in our greedy approach and the module 3, which is Dijkstra algorithm. And we know the Dijkstra algorithm is used for finding shortest path from a given node to all other nodes. I also given two resources from NPTEL talking about Dijkstra algorithm. So you can look at those as well, read about it, and get a better understanding of how things are. So primarily, why do we need such an application where we need to find the distance from source to all other destinations? So look at a case such as, let's say, a factory need to supply its manufactured goods to different godowns, and it goes via different cities or via different godowns. So it needs to know that what is the time it takes to deliver everything. Or you even look at, let's say, your water supply authority, Bangalore Water Supply, and to different houses or different places, is go via different junctions, different pipes. So how much and water will travel at a certain speed when it starts? What is the time it takes to reach every household? Something of that kind. So essentially, that is what we are trying to discuss and look at the application of the Dijkstra algorithm. Or you can even looking at our college. Let's say we are in the quadrangle, and for quadrangle you need to go to for each of the classes. You know the different path, and so we want to make sure what is the time it takes from quadrangle to go to each classroom, because for different classroom time could be different, assuming we have people walk at same speed and we know the distances, we should be able to figure out. And that's primarily the application of Dijkstra algorithm. So just to recap, we discussed graphs and trees, and we were discussing graph. We did discuss breadth first search and depth first search, the DFS, the depth first, and BFS is breadth first. That is what we discussed. And so we look at the how does that work out. So when we seen that when we do the graph traversal, both allows us to do graph traversal, and that's what essentially what we'll do when doing Dijkstra algorithm. And graph traversal in both the cases is done in order E time, and that is what we are seeing. We traverse each edge. Sorry. We look at each edge. My annotation is not working. Just. And we are also seeing that the if you do PFS and assuming my each, I'm looking at only in terms of edge, or if my all edge costs are same, then BFS can give me shortest path. I can go depth wise, then find the shortest path to each node. But if edges are different cost, then following a BFS
Acá,
does not work.
Daddy phone contact esto acá.
Yeah. Can you please keep your mic in the mute mode so that others don't get disturbed? Thank you. While doing DFS, depth first search, we see that it gives, if you do numbering and mark the nodes, the time we start exploring and the time we end the exploration, that is, we do pre-visit and post-visit work, that is when we can get interesting information. And we saw that if I look at pre-visit and post-visit marks, using those marks of values of a node, we can determine for an edge whether it is a back edge or a forward edge or a tree edge or a cross edge. And we have seen for a forward edge, pre-visit and post-visit mark of node U would contain the interval pre-visit and post-visit of node V if it is a forward edge or a tree edge. If it is a cross edge, they don't overlap. It's a backward edge, it is vice versa. For edge UV, the node V would contain the interval of node U and V. So go back to our tree traversal when we look at depth first search. And we do, when you look at Dijkstra, we look at how do we explore. Is neither going to be depth first nor going to be breadth first, but some kind of a different approach. That's what we'll take. So primarily our goal is given a graph, a weighted graph, that means each edge has a different weight, is connected, it could be directed or could be undirected. Our objective is to find the shortest path from given source vertex to each of the other vertex. And that is what we like to find using Dijkstra algorithm. And we know that path cost, so if I have a node, let's say A, B, C, D, E, F, and let's say these costs are 10, 5, 3, 4, 6, and let's say 7, 2, 11. If I were to look at my cost of path to from A to E, my A to E would be 4, my A to B would be 7, because cost from between A and B is, look at the minimum path A to E and E to B. So path cost is sum of cost of each edge on the path. If I'm taking a path AEF, cost of path A to F is cost of edge A to E plus cost of edge E to F. And that essentially what we'll look at and do that part. So Dijkstra algorithm primarily is, we follow, like, remember what we done in Prim's algorithm. Prim's algorithm was minimum cost spanning tree. What we did in Prim's algorithm was we pick up the node one at a time, keep building this tree, and then look at the edge, which is the lowest edge from the remaining nodes, and then make that node as part of the tree and keep growing. We'll take a similar approach, but difference will be we will not look at the cost of this edge, like we were looking at the cost of this edge X. Instead of looking cost of the X, we look at the overall distance from, let's say this is my source vertex. We will look at for all these nodes, let's say node P, Q, R, we will look at from given tree taken so far, what is the distance using this node to P, to Q, to R from S, rather than looking at only individual edge cost. We look at edge cost plus distance of this node so far, and that's the difference of Prim's algorithm from the Dijkstra algorithm. And that's what, so the difference lies in how do we compute the numerical labels. Previously, labels were, we were only looking at this edge cost to mark the label of a node. Here we look at labels from distance from node to a given node. And that is what basically the difference is. And we first look at the example, and then we will see how does it work out. So essentially, for a given node, we find from a given tree, find the vertex V, so that when the from U distance to V, so the node V would have a label, and we'll explain that in a while. So let's say I have a graph, I have a node here, A, let's say B, C, let's say this is 3, this is 2, and let's say this is 6, this is 5, and okay, let me say 30, this is 20, and let's say this is 5. Now we look at when we start with A, first we start from A, and we make the, now both B and C are reachable, so we'll make the distance of C as 20 and distance of B as 30. Now, because among B and C, C is the closest, we make C and make this A and C is part of a tree. And now from we look at what is the cost of B. We know the cost from A to B is 30, but cost from C to B is 5 and A to C is 20. So we look at minimum of 30 and 20 plus 5. This is what we'll basically look at, and that is what we are saying. We'll look at current distance value of the node plus the cost of the edge, and together that in Prim's algorithm, we were only looking at this, we were not looking at this. And that the difference lies between the two algorithms. And this will explain in a better example using that. So let's look at this tree. The graph consists of 6 nodes, and let's say we want to find from node A shortest distance to all the other nodes B, C, D, E, F, and that is what we want to find. We'll assume that distance from node A to itself is always 0. That means when we start with node A, distance to itself is always 0. That is what we start with. So we'll look at how do we construct single source meaning A is my single source, and shortest path to B, shortest path to F, shortest path to E, shortest path to C, and shortest path to D. So this is called single source shortest path. Single source shortest path. So single source shortest path to all other nodes, and that is what we'll basically look at. So let's start from A. When you start from A, we start from A, and now we set this distance of itself to basically 0. Select, and distance of it is 0, and we'll set distance of, start with distance of every other node to infinity. So distance of every other node will set it to infinity, and now we look at for this node. So this initialization part means whichever given vertex, set the distance of that vertex from itself to 0, and distance of every other vertex as infinity. This is the initialization part. Now we run in a loop n minus 1 times from A to all the other nodes, or we need to pick all the nodes. So we put the node, this node into the queue, we'll maintain a priority queue or any other method. So let's say we put node A into queue, and with respective weights. So initially my queue would have A of weight 0, B of weight infinity, C of weight infinity, D of weight infinity, and so on and so forth, and we find the minimum node. So from this, if you look at, we pick up A, and we pick up A and look at all the edges going from A onwards, so A to B, A to F, and A to D. Previous cost of B is infinity, but using A and cost of 3, so cost of A is 0 plus 3 makes it 3. So minimum of infinity 3 is 3. So we'll set the cost of B as 3, and that is what we'll basically set. We set the cost to 3. Similarly, cost of F is infinity. For A's cost is 0. So 0 plus 5 and infinity. So we'll look at infinity is the current cost. Infinity is current cost, and 0 plus 5 is 5. So min of these two is 5. So we set the label of F as 5, and that is what we'll basically do. and the cost becomes 5. Similarly, now we look at E. Current cost is infinity, but from A, 0 plus 6 is 6. So we set the cost of E to 6, and that is what we will do. Now my queue has 5 nodes. If you look at my queue, it has node B with a distance of 3, node F with a distance of 5, node with a distance of 6, C with a distance of infinity, and D with a distance of infinity. From among these 5 nodes, find the node with minimum distance, and if you look at minimum distance happens to be for B, DB is 3, so we pick this node B, and since we have picked up now, we look at all the edges going out from B. Previously we were looking at the edges, the cost. Now we look at all the edges going from B. So we have one edge B to C and one edge B to F. Now distance of B is 3. So if I reach C from B, I incur a cost of 1. So I need to look at current level of C is infinity. But if I go via B, cost of B is 3 plus I get 1.
3, 1, 4.
So 3 plus 1 minimum is 4. So my cost of C becomes 4, and that is what we would basically set the cost to C as 4. Same way we look at F. Current cost of labor is, if we look at 5, but if I go via B, cost of B is 3, cost of B to F is 4, that means via B it is 7. So mean of 5 and 3 plus 4 still remains 5. So we maintain this cost 5, we do not change it. So this cost remains 5. Now same way look at E, current cost is 6. Via B there is no edge, so that means we maintain this as a 6 and continue. So this remains 6. Now if I look at B is already taken, so from the given 4 nodes, cost of C is 4, cost of F is 5, cost of A is 6, and cost of B is infinity. Pick up minimum. So C happens to be minimum. We take C and look at all the edges going out of C. So this is 4, C to D is 6. So first we look at D, current cost is infinity, but if you go via C, cost of C is 4 and C to D is 6. So we look at infinity min of 4 plus 6, which is 10. Since this is using this becomes 10, we set this value to 10. And that is what we basically do. We set this to 10. And now look at C to F. Cost of C is 4 and C to F is 4. That means if you go via C, this would become 8. But I already have a cost of 5, so we will not update it, and cost of F remains 5. It does not change. And same way, there is no S C to F, C to E, so we don't change. So I'm left with 3 nodes now. From these 3 nodes, I look at the node with minimum distance. F is 5, E is 6, D is 10. So I pick F, which is 5. And again, look at the edges going from F. So this is 5, this is 2. So when I look at D, current cost of F is 5. 5 plus 5 is 10, is already 10. There is no point updating it. And similarly, F2 is 2, cost of F is 5, 5 plus 2 is 7, but here already have cost of 6. So this is going where F is more. We won't update it and we leave it there. And then I'll have to 2 nodes E and F. Minimum is 6. This minimum is 10. We pick E and proceed the same way. Every time we change the distance, like from infinity to 3, we look at which way I came, because I should know the path I build up. So when I updated the B, F, and E, I saw what is the preceded node. That means via which node I need to come. So for B, I'm putting A. For F, we are putting A. For E, we are putting A. But C, we are going via B. We're putting the predecessor of C as B. That means from A to C, you come via B, and B come via A, the cost of 4. Similarly, D, we are coming via C, so come, and then you see we'll put the value of C, and that's how we basically pick up. So for each node we specify, when we update the label, we also specify which is the previous node we came from, and that's how. So now we know, if we look at my shortest path from A to B is 3, A to F is 5, A to A is 6, A to C is 4, and A to D is 10. So I found shortest path by traversing the whole thing. Key challenge lies in, when I keeping the node with distances, how do I find the minimum? I'm always interested in finding the minimum, and that is what we know, that you like to have a find min, which is the most efficient, and we know that heaps, or the when use heap, find min. If I do a min heap, always takes order one time. And that means heaps are a best way to maintain finding this minimum distance. And essentially, that's what we look at. So let's look at does it really work correctly? Yes, we can prove by induction. Induction means if graph size is 1, distance is 0, that is the minimum, we are fine. And we are working with positive graphs only. And with induction, if it is true up to node k, then node k plus 1, we are always picking the node with minimum distance. Since the nodes are already covered, or nodes are already part of tree, they have minimum distance. So that means I have to pick a node which is the minimum distance. And we saw that if any other node we pick up, the distance will be larger. So using induction, we can prove that Dijkstra algorithm works correctly. Other thing you look at is the Dijkstra algorithm works only with positive weights. If, however, there are negative weights, it doesn't work. Like for this graph, in this case, if I were to use, given this graph of 3 nodes, assuming these are my weights, if I start with from A, first I'll pick A. A will be part of my starting node, starting vertex. Then I'll look at minimum. So DB4, I'll be adding B. Now that I added B, I know these are minimum. I can't change it, and then I basically pick up. But let's assume this distance, instead of 2, if this distance is -3. That means rather than paying cost, we're getting rewarded. So if I would do Dijkstra algorithm, first I would pick up B, but if I go via F to B, my cost is 2 and not 4. So that means, but B already has been taken as part of my tree, it cannot change. So Dijkstra algorithm works only with positive weights, and it does not work with negative weights. That's the point one should always remember and realize. Further, it works for both direct and undirected graph. It doesn't matter what kind of graph it is. So to look at how does my algorithm looks like, simplistically, I start with a connected graph, assuming graph V and E, and given a source vertex X. We assume that all edges are non-negative weights. And then once we go to dynamic programming, we'll look at Bellman-Fold algorithm, and we'll look at the Floyd-Wurzer algorithm to determine those work even with negative weights. But Dijkstra algorithm does not work with negative weights. And we maintain a label of dv for each node that maintains distance, shortest distance from node S to V. So we're starting with, we basically initialize a queue, and our performance or time complexity would fully depend upon what kind of queue it is. Queue is of basically vertices with their respective weights or distances dv. So this queue is, we'll maintain a queue of distances from source to each vertex v. So initialize queue means we're just setting header, there are no entries. And now for each vertex v, set the distance to infinity, and predecessor from source, that is the predecessor path, is to null, and we insert every node into the queue. That means all the nodes get inserted with a weight of infinity. And now we choose source vertex, set the distance to source vertex, and once we change the distance in the queue, decrease the distance dv of source to 0 from infinity. So do a decrease operation where ds becomes 0 from infinity. So at this point in time, ds would be 0, and for all other node dv, it will be infinity, what we are doing. And now we need to find the main loop of the algorithm, and we know the result null, that means from source I am reaching with DAA, and now the main loop starts. And we keep building my set of nodes, because once a node has been discovered, sort of we're not going to discover it. We will always look at nodes which already been discovered and nodes which are yet to be discovered. So the main algorithm part of it starts with a loop I0 to n minus 1, all the pick up all nodes, because we need to pick up n nodes. So first pick up the node with the minimum distance. Remember, when you initialize, when you done the initialization, we set distance of ds to 0, and distance of all other nodes was infinity. So delete min will give me node s, and now I pick the node and add this node to my nodes are discovered. And for all the edges which are going from this node u, but we're running in a loop, first time this u would be s, next time it would be some other node. So for all the edges going out from u, so all the edges u to w, we look at the weight of w, current weight of w, with current distance of u plus s cost of w. So if current weight of w, current weight of node u, which is what I picked up, plus the edge cost, if this current weight of the node which are big minimum distance plus the edge to the adjacent is w. So let's say my tree, this is the tree already picked up, and in the queue I picked up a minimum node. Now let's say from this I am going this edges, so I look at what the current label is. If this current label, let's say this is p, if the current label is less than, if the current label is more than this label plus this edge cost, so this label which is, let's say, node u, so du plus this c edge of this cost, so this label du plus c of uw, if current label of this node p, if current label is more than this, that means I should update the label, and that is essentially what we are doing. So we'll look at what, once you pick a node with minimum weight, we find all the edges such that adjacent to w, we find all the edges such that if current weight of w plus edge cost, if it is less than the current weight of w, then update that weight. Update that weight, define the predecessor as u, and decrease the weight into the queue, and so that when I come to the loop again, I'll basically pick up the minimum vertex. And that is what the basic algorithm is. And so look at each time the algorithm terminates, because each time we pick up one node with the minimum weight, and we keep picking up, and once we are run with loop n times, we picked up every node, and this dvu, the value, would contain the minimum distance. So look at the time complexity. Assuming if we are maintaining this queue, if this queue is unsorted array, this queue is unsorted array, then finding min will take me order n time, but decrease icon index would take me order 1 time. And I'm doing this, searching for this for the entire graph will take me order e time. But I'm running outer loop n times, this outer loop n times, but finding the delete min, performing a delete min will take me order n time. So I'm running the loop n times and I'm doing this n time. So my time complexity becomes order n square. That is when if I do unsorted array. If, however, I maintain Q as, let's say, min heap, when I maintain my Q as min heap, that's what we discussed 2 lectures ago. Now, find min is order 1, but delete min takes order log n time. My find min takes order 1, delete min, because it has to adjust, takes order log n time. So this operation for, and this loop is n times, this gives me order, so this plus this gives me n log n time. But further you look at, you are looking at adjacency list each edge here, and for each edge we might decrease the weight. For each edge we might decrease the weight. So in a heap, in a min heap, if we decrease the weight of a W, that may again take log n time. So, and this we are doing for each edge. So my time taken is order n log n for this. Remember, this is n loop. So order n log n for delete means, and decrease will take me time order e log n, or we can say m log n, and e is generally more than n. So time taken Dijkstra algorithm would be order e log n, and that is what we basically say. If you are doing adjacency matrix using unsorted array, we already said time taken would be order n square, and because decrease takes this, but minimum it takes order v time, hence it is order n square. If you were to use as adjacency list and we maintain using min heap, then outer loop is again order n times. Delete min takes order log n time, so that means this takes order n log n time. But for each edge, when you decrease take log v time, and we are doing for each edge, so this takes e log v time. So time taken is order e log v plus v log v, which is basically e log v, and the time complexity of Dijkstra algorithm. Is it a greedy approach? Yes, it is a greedy approach, because what is a greedy approach? In a greedy approach, we make a sequence of choices, and once a choice is taken, this choice is never changed. And what is our choice? Using some greedy approach to pick the choice. In Dijkstra algorithm, we are making a choice with minimum distance from source. Sorry, typo there. Minimum distance from source. Let me just correct this. So we take minimum distance from the source, and once we pick up a vertex, we never look at the distance again. So in that sense, it is a greedy approach, and we also find greedy approach gives me the optimal answer. We are basically done with Dijkstra. Now few questions I would like you to go through a variant of Dijkstra algorithm. So one example is, suppose if I were to basically do that, my graph was, let's say, undirected graph, but I convert into directed weighted graph. Do I need to change anything in my Dijkstra algorithm? So what we taken the example of 6 nodes, we taken the example of undirected graph. Undirected graph means the cost of u to v or u to w is same as cost of w to u. But if it is a directed graph, the two costs could be different, means cost of as uw is not equal to cost of w comma u. For example, I take node A and I take node B. this cost could be 4, but the cost from B to A could be 6. So this directed graph, that means they have different cost. Question is, if I have a directed graph, do I need to make any changes to the Dijkstra algorithm? And look at the whole algorithm, we really never bothered about whether it's a directed as or undirected as, looking at the essential list. So algorithm would work as it is without making any change. Doesn't matter whether it's directed graph or undirected graph. Second question, let's say we need to given a graph, we're given a graph, let's say we're given a graph A, B, C, D, E, F, G, H, and let's say we want to find minimum distance between D and E. So given a graph question is, we need to find minimum distance from D to H, let's say D to E, minimum distance from D to H. Using Dijkstra algorithm, how would you go about? Any answers? Given the random graph or any graph, I need to find distance between two vertices. Let's say given this graph, I would like to find the distance from D to the vertex H. Using Dijkstra algorithm, how would we proceed? Anyone like to answer? Either you can use your mic or you can type in chat box. Both are fine. Aisha, Jana, anyone like to answer? Yaswant K or Yaswant G? Is question clear? Anyone like to answer? That given this graph, we have to find using Dijkstra algorithm minimum distance from D to H. Anyone like to answer? Tarun or Sweta? Just think about how would you proceed this problem. No one. So essentially all we need to do is, rather than starting from graph node A, make D as my source vertex. So make D as source and start computing distance to all other nodes till we find H. So the only change we'll make it, if you look at the algorithm, the only change we'll basically make in the algorithm is set the source as D, and in this loop for I0 to V minus 1, for I0 to V minus 1, we'll say or till we find till the node H is part of my VT. So this till we find T, and that is what we'll basically do to solve the second problem. So let's do another question there. So question 3 is, This is also called single destination shortest path problem. Basically means is for a given node somebody's mic is in on. Can you please put it off? So given the graph, so again given my graph, for this node, let's say node X, so sorry, given my graph, I would like to find the shortest distance for the node, let's say this node P, from all other nodes. So this is a directed graph. For a directed graph, we would like to know what is the shortest distance to node P from all other nodes. So we are doing Dijkstra algorithm as a reverse. Essentially what you're doing is Dijkstra algorithm for a given node, we are finding shortest distance to all other nodes. Now taking the reverse problem, we are saying for a given node P, find the shortest distance to P from all other nodes. It is the reverse of Dijkstra algorithm, and this is also called the single destination shortest path. If we know that we can find from P to all other nodes using Dijkstra, but then directed graph, it may not be same. The approach is convert this problem into Dijkstra algorithm problem. So what we do is take the graph and reverse all the edges. So if edge was like this, make the edge, reverse the direction of the edge. Once you change the direction of the edge, now from the node P, run the Dijkstra algorithm and find the shortest distance of from P to all other nodes, and that will basically give you the shortest distance of all other nodes from all other nodes to P, because within the graph reversal, that means actually we'll take this edges, and that is what we call a single destination path. My next question possibly is, let me go to the next question. Let's say we what is called as solve the single source in a graph with non-negative numbers. So rather than giving a edge cost of edge, let's say you are given the cost of visiting a node. So assuming a graph A so rather than giving cost of each, the edges, we say once you visit a node, there's a cost you pay. Let's say cost is given as 10 to A, 5 to B, 11 to C, E is 20, D is 6. And we want to find what is time to take in visiting node, what the cost will pay. So can we convert this into Dijkstra algorithm? Basically, look at the edge, look at the nodes, and define the cost of the edge as sum of the two weights. So this edge becomes 15, cost of this edge becomes 21, cost of this edge becomes 25, this edge becomes 17, and this becomes 26. Now I have cost of each edges, and I can run my Dijkstra algorithm, and that will give me the minimum cost. So you can use Dijkstra algorithm with different ways to solve the problem. Understand the difference between Dijkstra versus Prim algorithm. Prim is for minimum cost spanning tree. Dijkstra is single source shortest path. Though both of these give you kind of a tree, but the two trees could be completely different. Let's take our case of the example we have taken. If you were to run the Prim algorithm, that's the tree basically we get. But if you look at the cost of spanning tree is, this spanning tree is 3 plus 4 plus 1 plus 2 plus 5, which is 7 plus 1, 8, and 2, 10. So cost is 15. The minimum cost of this tree is 15. And so, and Dijkstra algorithm, if you look at, this is the tree basically I get. And if you look at cost of this tree is, so cost of this tree using Prim algorithm is 15. Cost of, if I were to take this tree and take the cost of the tree, this would be 3 plus 1, 4 plus 5, 9 plus 4, 15, 4 plus 10, 14 plus 6, 20. So cost becomes 20, their cost is 15. But if I look at the shortest distance using, so look at distance of B is 3, distance of C is 4. So let me, if we were to look at, this distance is 3, this distance is 4, this distance of F is 7, distance of going with this path is 7 plus 2 is 9, and this distance is 3 plus 4, 7 plus 5 is 12. So the total distance is 38, whereas in this case is 28. So the two algorithms is Prim is basically cost of spanning tree. We look at cost of each as, but Dijkstra algorithm is we look at minimum distance from source to all other vertex A to B. Sorry. We look at A to B, A to F, A to F, A to D, A to E. The two are different purpose and one cannot apply the other. So in a summary, what we essentially done, we looked at the Dijkstra algorithm and we say we always keep shortest length for each vertex from the source, and once a node is taken we never change it. We also maintain predecessor to determine the path. It is different from Prim's algorithm because in Prim's we choose the vertex only with shortest length from the tree and not the shortest length from the source. In Dijkstra we look at shortest distance from the source. In Prim we look at shortest distance from the tree, not from the source, and that's the key difference. So I'm done for today. If you have any questions, please feel free to ask. If not, next week we'll start with dynamic programming, and over the weekend I'm going to give you the third assignment. Please go through it and we can discuss anytime. So any questions, please feel free to ask. Otherwise, I'm done and you can sign off. Thank you.